This module will guide us through database management using MongoDB, a popular NoSQL database system. We will explore NoSQL concepts, CRUD operations, Mongoose ODM, and the aggregation framework for data analysis. Let's begin by understanding the significant advantages that NoSQL databases offer over traditional relational systems. NoSQL provides flexible, scalable, and high-performance data storage solutions which are crucial for modern applications. First, NoSQL databases boast a schema-less structure, meaning no predefined table structure is strictly required. This flexibility allows for agile development and easy adaptation as your application's data needs evolve. Next, NoSQL offers excellent scalability, effortlessly handling massive data volumes through horizontal scaling. This means you can distribute your data across many servers to manage growing demands efficiently. You can also choose from flexible data models, storing information as key-value pairs, documents, or graphs. This adaptability allows you to select the best model for your specific data and application requirements. Furthermore, NoSQL databases deliver high performance, optimized for incredibly fast read and write operations. This efficiency ensures quick data access and modification, critical for real-time applications. Lastly, their distributed architecture means data can be spread across multiple servers, enhancing fault tolerance. This setup ensures high availability and resilience, even if some parts of your system fail. Now, let's delve into understanding the different types of NoSQL databases, each designed for specific data needs. These diverse models cater to varied data requirements, offering specialized solutions beyond traditional relational databases. First, we have document-based databases, which are quite popular and store data in JSON-like documents. These documents are flexible and can contain nested structures, making them very versatile for complex data. Well, excellent examples of document-based databases include MongoDB and CouchDB, which you'll encounter often. Next, key-value stores use simple key-value pairs for data retrieval, offering extreme speed and simplicity. Imagine a dictionary where each unique key points to a specific value, allowing for very fast lookups. Popular examples here are Redis and DynamoDB, often used for caching and session management. Then, column family stores are optimized specifically for analytical queries and handling large data sets effectively. They store data in columns, making it efficient to retrieve specific data attributes across many rows. Cassandra and HBase are prominent examples of column family stores used in big data applications. Finally, graph-based databases excel at representing and managing complex relationships between data points. They model data as nodes and edges, making them ideal for social networks or recommendation engines. Neo4j and ArangoDB are leading examples of graph databases, perfect for interconnected data. We will begin by exploring the core characteristics of MongoDB, understanding what makes it a powerful NoSQL database. It is an open-source, document-based NoSQL database, known for its flexibility and scalability in handling data. First, let's discuss its document-oriented nature, which is a fundamental aspect of how MongoDB stores data. MongoDB stores data in flexible BSON documents, which are binary JSON-like structures, allowing for rich and varied data. These documents are self-describing and hierarchical, meaning they contain all necessary information and can have nested structures. Next, we'll examine its schema-less design, a key feature that provides immense flexibility in data modeling. This means no rigid structure or predefined schema is required, allowing for dynamic and evolving data definitions. Such flexibility greatly supports agile development methodologies and accommodates evolving data requirements with ease. We also note MongoDB's high scalability, which is crucial for modern applications dealing with large data volumes. It easily handles large-scale applications by efficiently managing and distributing massive amounts of data across systems. This database specifically supports horizontal scaling, distributing data across multiple servers to enhance performance and capacity. Finally, let's consider its high performance, a critical attribute for applications demanding quick data access. MongoDB is highly optimized for fast reads and writes, ensuring quick retrieval and storage of information. It effectively supports indexing, which significantly helps to speed up data retrieval and query execution times. Let's compare MongoDB with traditional SQL databases, highlighting their key differences in structure and queries. We will examine how these two database types differ in their data models, query languages, and scaling approaches. We compare them across several important features, providing a clear overview of their distinct characteristics. First, let's look at how schema is handled in both SQL and NoSQL databases. Next, we compare their fundamental data structures, which is a significant differentiator. The query language used to interact with these databases also varies considerably. We'll also consider how relationships and join operations are managed in each system. Finally, we compare their approaches to scalability, a critical factor for modern applications. On the SQL side, representing relational databases, we see a more traditional approach. SQL databases enforce a fixed schema, meaning you must define tables and their columns strictly upfront. Data is organized into tables with rows and columns, following a very structured tabular format. They primarily use SQL or structured query language for all data manipulation operations. SQL databases fully support join operations to combine related data from multiple tables. Scalability in SQL is typically vertical, meaning you enhance performance by adding more CPU or RAM. Now, let's look at MongoDB, a prominent example of a NoSQL database, and its unique features. MongoDB is schemaless, storing data in flexible JSON-like documents that can vary in structure. Data is organized into collections, which hold JSON-like documents, offering great flexibility. It uses the MongoDB query language with commands like find and insert 1 for data interactions. Instead of joins, MongoDB often embeds related data directly within documents, simplifying retrieval. MongoDB excels at horizontal scaling, distributing data across multiple servers to handle large loads efficiently. We will now focus on mastering MongoDB CRUD operations, which are fundamental for effective data management. These operations represent the fundamental actions you perform to manage and interact with data in your database. The first operation is create, which involves adding new data to your MongoDB collections. Specifically, you use the create operation to insert new documents, essentially records, into a chosen collection. Next, we have the read operation, essential for retrieving information stored within your database. This allows you to retrieve specific data or all data from a collection based on your query criteria. The update operation enables you to modify existing data, ensuring your records remain current and accurate. With update, you can modify existing documents, changing field values or adding new fields as needed. Finally, the delete operation is used to remove data that is no longer needed from your database. This action allows you to remove specific documents or multiple documents from a collection permanently. Now, let's explore essential MongoDB command line operations, allowing you to interact with your database directly. These commands provide a powerful way to manage and query your MongoDB data using the interactive shell. To begin, you need to start the MongoDB database server, which runs in the background. You achieve this by simply typing the command MongoD into your terminal. Next, you'll connect to the interactive MongoDB shell, which is your primary interface for commands. Just type Mongo in your terminal and you'll be connected to your database instance. You can then create a new database or switch to an existing one for your operations. This is done with the user command, followed by the database name like usemydatabase. To insert data, you can add a single document into a specified collection within your database. This code uses db.users.insert. Want to add a new user named Alice with her email and age. You can easily retrieve all documents from a collection to view their contents. The db.users.find command will return every document stored in the user's collection. To modify data, you can update a specific field within an existing document. Here, db.users.update. One finds Alice and sets her age to 26 using the set operator. Let us explore the key capabilities of Mongo's ODM. a powerful tool for MongoDB. Mongoose brings structure and validation to MongoDB, especially when working with Node.js applications. One core capability is schema-based modeling, which helps define the structure of your data. This feature defines the structure for MongoDB documents, ensuring your data adheres to a consistent format. By enforcing a schema, Mongoose ensures consistency and reliability across all your database data. Another important feature is built-in data validation, which safeguards the integrity of your information. It ensures data integrity by validating data against predefined rules before it is saved to the database. Mongoose supports various validation rules, such as required, unique, and minimum or maximum values for fields. We also have middleware support, often referred to as hooks, for executing functions at specific points. These hooks allow code execution either before pre or after post database operations, providing great flexibility. This can automate tasks like password hashing, logging, or other processing before or after data changes. Mongoose also offers simplified query helpers, making your database interactions much more straightforward. It provides convenient methods such as find, find one, and update one, simplifying common database queries. These helpers offer a cleaner, more readable application programming interface for interacting with your MongoDB database. Lastly, let's look at population for relationships, a powerful feature for managing linked data. Population supports join-like referencing, allowing you to establish connections between different collections in MongoDB. This capability enables Mongoose to seamlessly fetch and integrate related documents, simplifying complex data retrieval. Let's now look at defining schemas and handling validation, structuring data, and ensuring integrity with Mongoose. We will see how Mongoose helps in structuring your data and enforcing validation rules for robust applications. Here, we define a user schema, outlining the structure and validation rules for our user documents. Fields like name and email are required. Email must be unique and age has a minimum value of 18. This code defines the user schema with required fields, a unique email, and a minimum age for users. Next, let's look at how to handle validation errors gracefully within an express route. If invalid data is provided, Mongoose throws an error which is caught and returned to the client. This express route attempts to create a new user and returns a status 400 error if validation fails. Now, we'll explore the aggregation pipeline stages, powerful tools for transforming and analyzing data within MongoDB. These stages allow you to perform complex data transformations and analytics directly within your database. The match stage is used to filter documents based on a specified condition similar to a where clause. It passes only the documents that satisfy the criteria to the next stage in the pipeline. The group stage groups documents by a specified identifier and performs aggregation functions. This is useful for calculating sums, counts, averages, or other aggregate values for group data. The sort stage arranges documents in either ascending or descending order based on one or more fields. This helps in ordering your results for better readability or for further processing in the pipeline. The project stage, it allows you to select only the data you need, effectively transforming the document structure. The limit stage restricts the number of documents passed to the next stage in the pipeline. This is useful for paginating results or simply fetching a fixed number of top documents. The skip stage ignores a specified number of documents, effectively offsetting the results. Combined with limit, skip is also very useful for implementing pagination in your queries. The unmin stage deconstructs an array field from the input documents to output a document for each element. This creates a separate document for each array element, making it easier to process array data. Finally, the lookup stage performs SQL-style left-outer joins between collections within the same database. This allows you to enrich documents in one collection with related data from another collection. Let's summarize the key takeaways from this module on MongoDB database management. We've covered essential concepts, crucial for effectively managing and interacting with your MongoDB databases. NoSQL databases provide flexible, scalable, and schema-less data storage, ideal for modern, evolving applications. MongoDB is a document-based NoSQL database that stores data in JSON-like BSON documents. CRUD operations are fundamental for data interaction, allowing you to create, read, update, and delete documents. Mongoose offers schema-based modeling, validation, and middleware to structure and validate data in Node.js. The aggregation framework enables powerful in-database data transformations and analytics through a pipeline of stages.